So I want to take a closer look at this circuit that we considered in a previous video where we were looking at how to use supernodes to help with our node voltage analysis. So let's say we wanted to make things a little easier on ourselves and not have to use a supernode. Well, we could either choose to redefine our reference nodes, or maybe our reference node and node voltages weren't given to us and it was our choice. So we can see we have three essential nodes, so three places where we have three or more elements connected. Of course, we also have a non-essential node over here in the top left, but we're not going to worry about that because it's not going to be relevant. We notice we have two voltage sources, 14 volts and a 6 volt. The 14 volt has a 4 ohm resistor that is in series with it. So we know that's not going to be an issue if we're trying to write currents going through that 14 volt source. However, our 6 volt source is all by itself between these two essential nodes. So what we could do to make things a little easier on ourselves is we could define one of these top two essential nodes to be our reference. So let's say we make this top left node our reference node. So then, of course, we could define this top right node as being node 1, and this bottom node as being node 2. So we have then, this is our node voltage V1, and this is our node voltage V2. So note, our negative polarity of our node voltages is still at the reference node. So that's very important. Even though I have our reference node in the top, our negative polarities are still at that reference node. Okay, so let's see how much easier this is now that we don't have to use a supernode. So of course, like we saw for our bridge circuit example in a previous video, now we can just say that our node voltage V1 is simply equal to 6. So this would be our node 1 equation. And so let me take a step back too, and we know that we have three essential nodes, so therefore we know we're going to be expecting number of essential nodes 3 minus 1, 2 equations, the same as we saw when we worked this with the supernode. So we see our node 1 equation is extremely simple. Our node 2 equation we can get using the same techniques that we have used before. It's maybe a little less straightforward for this current coming out this direction, but we know this current is coming out here and going in this direction, and we could define some voltage like this. And so what we could do then is we could say we have that current, and that current is equal to the voltage V over our 4 ohm resistor, and we'll come back to that here in a second. And then we also have current going up through that 3 ohm resistor from Ohm's law is just V2 over 3. And our current going out the right, we're going to have current going out sort of two branches there. We're going to have V2 minus V1 over 2 going through the 2 ohm resistor, and V2 minus V1 over 6 going through the 6 ohm resistor. And so like I mentioned in the previous video, of course we could just combine the 6 and 2 ohm resistors in parallel, but because we're looking for I, we'd ultimately have to separate them out again at the end. So whatever you prefer to do is fine. So now we could come back, we need to figure out what to do with this voltage here to get that in terms of our node voltages. And so of course what we can do is just a KVL around here. So if we do that KVL, what we can see is this is going to be equal to, so V is equal to 14 plus V2. So we have 14 plus V2. If we put that in place of our V, so we have 14 plus V2 divided by 4. If we want to simplify this, we can multiply by 12 and collect terms. So multiply by 12, collecting terms, we end up with negative 8 V1 plus 15 V2 equals negative 42. So in this case, of course, we could still use the matrix method, but this is just almost too simple to even pass up. We can just plug in our 6 for V1 in our second equation. So of course, we can just take this V1 equals 6 and plug it in for this V1 here, solve for V2, and what we'll get is V2 is equal to 0.4 volts. But remember, ultimately we want that I. So now what we do is we could solve for our I, And we could either look at this expression here, which was equal to negative I, because remember this would have been the current coming out of our node of interest going through here, just like we also had a current going through here and a current going through here. Or we could just use our sort of KVL and our Ohm's law to redo that whole step. Either way you do it, you should arrive at I is equal to V1 minus V2 divided by 2 ohms, which is equal to 6 minus 0.4 divided by 2. So if we plug that in, we get 2.8 amps, which is, of course, the same thing that we got when we used our Supernode technique. So obviously a lot less work going in here, so it can be worth taking a minute before you start the circuit to think about what's the best choice for my reference node. One other thing I'd like to point out is, of course, this V2 equals 0.4 and our V1 equals 6 are not the same as the V1 and V2 that we had when we used the Supernode technique. And that shouldn't come as any surprise because, of course, our V1 and V2 are defined very differently from how they were in the previous circuit. Okay, so that's all for this example, but if anybody has any questions about how to choose a good reference node or how to do any of this analysis, please don't hesitate to let me know.